So, good evening, everyone. I am here to start the doubt solving session of the course Introduction to Composites. So, the assignment of week one is as follows. The first question is about the polymer which will have low cost and high operating temperature. So the operating temperature mainly depends on the melting temperature of a polymer, and the melting temperature would be higher if its bonding is higher than the others. So as we can see, these are the four polymers which were there in option. First is the polyether ether ketone, whose structure is given here. It has ketone group along with two ether groups. Then the second option was polyphenylene sulfide, which is simple phenyl ring with sulfur at the end. And the third one is nylon, which is commonly known by all of us. It's um, a amide group. And the fourth one was PTFE, that is Teflon. So as we can see, among all of these structures, the structure which would probably have highest bonding and will melt after a lot of time would be PEEK, as its structure is quite complicated and the amount of bonding which is possible in PEEK is also higher as compared to the other three structures. And also from the literature, we can see that its operating temperature is 260 degrees Celsius. Teflon also has a operating temperature of 260 degrees Celsius. However, the melting point of Teflon is comparatively lower as its size is smaller. So it's easier to melt it because the overall chain, the monomer of this chain only consists of two carbon atoms, while that of PEEK is quite complex as it has three benzene rings, and therefore the operating temperature of PEEK is highest. Um, and thus the answer to this question would be PEEK. So the next question is about the polymer which will have maximum strength. So, from basic chemistry concepts, we already know that the strength of the polymer mainly depends on its molecular weight, the size of its chain, and the amount of cross-linking which is there within the polymer after the polymerization is complete. So, these are the four available options. The first is the phenolic ring. It's quite simple structure. The second is the epoxy ring. It has a lot of oxygen atoms and contains few benzene rings too, with epoxy rings at the ends. The third is the polysaturated, no, unsaturated polyester resin. It has a lot of ester units, that is a lot of oxygen atoms to have van der Waal or hydrogen bonds, and this polymeric chain can also have a definite amount of cross-linking. And the fourth one is polyamide. So polyamide is quite simple ring. It has just amide rings with single phenyl ring. So we can see out of the four available options, the uh, one which will have highest amount of cross-linking would be the chains which are comparatively straighter and have more sites for efficient hydrogen bonding or van der Waal bonding, or just simple covalent bonds and introduction of hardener units, or like other polymeric chains. So therefore, out of the available options, this epoxy ring would be uh, the polymer with highest strength, as it has a comparatively simpler chain structure. Therefore, cross-linking is easier, and the um, uh, chain is overall stronger with higher strength. The following one would be USP resin. This is weaker than the epoxy resin because its chain is more haphazard. So cross-linking in terms of bonding between consecutive layers is difficult in case of USP resins. Therefore, the answer to this question would be epoxy polymer, which has typically higher strength. So the third question was on the term which is used to define single fibrous composites. So composites are normally a combination of two or more components which combine together to form a macroscopically homogeneous substance, which can serve our purpose for which the composite is being designed. So, if we talk about fiber reinforced composites, that is in which the fibers bear the load while the matrix material just transfers the load from one fiber to another. In those cases, the angle at which the fibers are laid define the properties of that particular laminate. And if the this is the entire stack of laminates, which is all stacked one over another to define the composite laminate. But if we consider only single fibrous composite out of this, then this is termed as lamina. The combination of all of these together would be termed as laminate. This is a very common term when defining a composite, and thus its answer would directly be lamina. Then the fourth question is about the longitudinal modulus of lamina. So, when we define strength of any composite or any material which has properties in like different properties in different directions, then they are known as anisotropic materials, and in those cases, two moduluses are defined. One is longitudinal modulus, in which the stress generated in the system along the direction of the force which is applied is recorded, and that is termed as longitudinal modulus. But in case of transverse modulus, that is the other kind, uh, the stress is recorded in the direction which is perpendicular to the direction where force is applied. For instance, um, if this is a straight fiber. Then, if we pull the fiber in this direction and and we record the stress along these directions only, then these are known as the longitudinal stresses, and the stress at which the fiber will break on application of this particular force will be termed as the longitudinal uh, strength. And similarly, the slope of the graph between stress and strain will give us the longitudinal modulus. But when we are applying force in this direction and measuring stress in the directions which are perpendicular to this particular direction, these are known as transverse components. So if we apply force in this direction and measure the entities along the perpendicular direction, then those are transverse modulus. And in case of composites, the longitudinal modulus, that is along the force of application while measuring the property, then the longitudinal modulus depends on the longitudinal modulus of the fiber, the matrix component, and the fiber volume fraction in that particular composite. So this is defined by the Hafen-Sai equation, and this equation is defined here. So E1 is the longitudinal modulus, EF is the longitudinal modulus of the fiber, VF is the fiber volume fraction, EM is the longitudinal modulus of the matrix component, and VM is the matrix volume fraction. So as we can see, the longitudinal modulus depends on all three entities. Therefore, the option would be all of these. This is a correction in the assignment as it has been accidentally marked that the right answer is some other, but the correct answer is all of these. That is fourth. So now we are at the fifth question. In this, it is asked that for experimentally determining the fiber volume fraction of voids, which of the following test can be used? So this picture, the first picture, mainly illustrates the cross section of the composite which we manufacture. So we can see these circles are the fibers which are laid in particular direction, and this dispersion media is the matrix, that is our resin. So once we enlarge this, we have this reinforcement and we have resin. Now we also have some air voids present in between, like this small air void here and there, which we can see, and this is a similar picture. In this we can see there are a lot of air voids. So the percentage of volume of this air void is termed as the void volume fraction. So for measuring this, we simply take this composite, measure its volume as a whole, we measure its weight, and then we burn it at a temperature such that the resin will melt out of this entire combination, and we'll only have fibers present at the end. So this is the image of the composite. Once entire resin is evaporated out of it, and we only have fibers present in the system. So now we will have the mass of the fiber which would be present in the system. We also know the total mass of the composite. So the mass which is evaporated is the mass of the resin. We also know the volume which is there initially. Once we compare all of them together, we can have um relationships between the density such that the volume of individual components would be determined from this by dividing the overall mass by the density of individual components. Once we have the volume fractions of fiber and the resin, we can subtract these volumes by the total volume to determine the volume of the void components. And therefore, the answer to this question would be 5, that is burn or acidization test, which could be used to determine the volume fraction of voids in a given composite. So that's all for